The other thing I want to talk about in addition to outer sphere reaction is an inner sphere reaction. Unlike outer sphere reactions, inner sphere reactions are, have strong interactions between the reactant and product, or in an electrochemical sense between the, say, the electrode surface and the material. Electrode and ion or molecule. Usually it involves bond breaking or making as concerted with the electron transfer process. In other words, often we'll think about two reactants getting together and form a bond or form a significant amount of electron density in order to get that reaction to occur. These are these adiabatic type reaction processes that we talked about. So we make perhaps an electrode species complex. Often molecules, for example, will exist as adsorbed species on electrode surfaces, and that would be a system where we might have an inner sphere. What we find also is that with inner sphere reactions is they tend to be strongly dependent on electrode material. And that makes sense. If we're talking about making or breaking bonds between the material and the electrode itself, we expect the electrode material that it's made of to be involved in that, and the electrode material would be important. The prototypical inner sphere reaction is the reduction of protons. So if we take a look at that, here's where a system where we do see a very significant interaction of the electrode material with the proton. We've already talked about this a little bit. We said, well, mercury, the reduction of protons on mercury is very slow, but we see the reduction of mercury on platinum is very fast. And so here already we see signs of perhaps an inner sphere process. We see a dependence on the rate of the reaction on the electrode material. Remember that the overall reaction is 2 protons plus 2 electrons going to hydrogen gas. There's going to be a bond formation there, so that's already another indication we might have an inner sphere process. Now, in order for this to be, have 2 electrons, we need to really have to have a multi-step process. We don't ever really see in electrochemistry 2 electrons going in simultaneously. Whenever we have 2 electrons, we're going to have 1 electron, a reaction, and another electron at the second point. There's never a simultaneous 2 electron transfer and electron transfer processes. So if we have 2 electrons going into that system, we have to have a multi-step process. There's 2 basic possibilities. We can think about a proton plus an electron going to a hydrogen radical, hydride, and then 2 of those hydride materials getting together to form hydrogen gas. And you can see we need 2 electrons to form the 2 hydrides, or the 2 hydrogen atoms. Or an alternate process is if suppose we have hydrogen hydride plus protons going to H2 plus, and then H2 plus electrons going to hydrogen gas. In either case is okay. This might actually be a more favored reaction under some conditions, depending on the concentration of protons in solution. These are second order processes, you see, and so it would depend a little bit on the concentrations. One of the things you can think about in this particular reaction is changing the overall rate of the reaction by considering the fact that the proton must go to some higher energy state, this hydride. We don't see these in solution, so they must be a higher energy than the protons. And then it can be, go back to a lower energy state, the hydrogen gas. What can happen, though, is we can stabilize that species by forming hydrogen that's absorbed onto a metal surface and then going back to the hydrogen gas. And so there is a change in the energy there, that's the free energy of absorption, that can be taken into advantage. And so it requires less energy to get this reaction to go if we can absorb that hydrogen atom, hydrogen radical onto a species. So if we have an absorption process, the reaction would be something like this. Where we have a metal hydrogen adsorption. In fact, you could think of it as a bond being formed, a metal hydride being formed on the electrode surface. We haven't talked about multi-step reactions. We'll talk a little bit more about them later on, but let's think about a multi-step reaction where we have more than one electron transfer involved in it, and what impact that has on the rate constants that we can observe. There's two basic ideas that we can think about for multi-step reactions. And just like any kinetic situation, they'd be the same. In the first case, for example, all the steps are fast. There's really no extra energy required. No extra energy, activation energy is required because we've already put in enough energy to get to the one state to do all the rest of the process. In that case, we can use the standard formulation. In other words, we can write the Butler-Volmer equation and put in for N2, and that would give us the proper result. In other words, the rates of reaction are fast enough that we can do that situation. The second case is where there is a rate determining step. I always forget to write the last word there. Can use standard formulation. In other words, Butler-Volmer equation. In that case, there is a situation where we have to distinguish between the number of electrons that are involved in the overall process and the number of electrons that are involved in the rate determining step. Because there's a rate determining step, the kinetics are going to be strongly influenced by the number of electrons involved in the rate determining step and not the number of electrons involved in the overall process. So we can rewrite our expression for a Butler-Volmer equation for the current in this case is NFA K0, that's the same as before. C0, x equals 0, that's the same. E to the minus alpha, and then we put in a subscript apparent, and then the rest would be the same, and then minus C sub r E, and then 1 minus alpha apparent F E minus E0 prime. And what we see is that if the first step is rate determining, then alpha apparent will be equal to 0.5. In other words, the first step, because it's the kinetic step, is setting the alpha for the whole thing. And so we just set an alpha just like we would see for a first step process. Or it would be somewhere around 0.5. It could vary from 0.5, just like a normal electron transfer process could vary. But we would expect alpha apparent to be from 0 to 1, just like we saw for one electron processes. However, at the second step, is rate determining, alpha apparent will be equal to 1.5. In other words, we see an alpha value that's more than 1, which is not what we said alpha could be. But because the first step is very fast, it basically just adds on to that process, and we see an alpha apparent 1.5. And so we can use Tafel plots to understand mechanistically what's going on. And since the proton reduction is such a fundamental process, people have done this a lot. And what we see is that for hydrogen ion reduction on, say, platinum, gold, copper, and mercury, we see basically in the order of their electrode reactions going lower. So platinum is very fast, the fastest rate. Gold's a little bit slower, actually quite a bit slower, but still pretty fast. Copper, much slower. Mercury, very slow. We see alpha apparent values of 1.5, 1.3, 0.5, and 0.5. So what can we say about the mechanism when alpha is 1.5 on platinum electrodes? Well, it suggests that there's a multi-step reaction, and that the first step is not rate determining. The second step is rate determining. So if we go back to our expression, let's suppose this is going on. We've got a hydride formation, and in fact we're forming a metal hydride. So what we're thinking about in platinum is that we form this metal hydride, and that is rapid. And then what's slow is getting those two metal hydride species together on the platinum surface for the reaction to occur, and then being removed from the surface, basically, which is probably the slow step. So desorbing is probably the slow process on that particular case. On the other hand, copper and mercury are very slow, and that suggests that the hydride formation is the slow step. In other words, it takes a lot of energy, and we go back to here and we can think, because we're probably in mercury and copper, we're not absorbing the hydride on the metal surface, so the activation energy is very large, and so once we form the hydride, we have enough energy to do the rest of the process right away. The second electron transfer can come in right away. And so for copper and mercury, we don't see that absorption system. So here we see a prototype that would be an inner sphere reaction. And it'd be interactive. There is a strong dependence on metal on the rate of the reaction. Here is less so and more like an outer sphere process, a non-interacting metal. So here we see the inner sphere is actually faster than the outer sphere, but that's just because we've got this additional energy that's supplied basically by the absorption of the metal to the metal. In contrast to the proton reduction, which is a 2-electron process, multi-step process, usually when we have single electron transfer processes, they tend to be relatively rapid. An example I show is this one, which is for trans-stilbene. Where we have a situation where we have a double bond and a benzene rings associated with it. That particular case, forming a radical anion. Whoops, that's not how I want to do that. You can think of this as being as the electron being delocalized amongst that aromatic double bond aromatic process. And so that simple process requires very little bond bending or breaking, very little bending on the system. It's fast. There's small solvent interaction because that's a fairly large molecule with the benzene rings attached to it, and so on. And we can actually understand that this reaction has this delocalized character by doing some simple steps. Because we can both oxidize and reduce stilbene, it's a pretty good molecule. For example, to oxidize this, we can actually change the potential for oxidation by adding groups that will subsequently add electron density to the system. For example, starting with, say, a methoxy group, or an amine group, or a dimethylamine, or electron donating. And so we'd expect that by applying electron density to this system, by having these groups attached to the phenyl rings, we should make it easier to reduce, or oxidize, I should say. And we can see changes in the waves for the oxidation potential in that particular case. On the other hand, we can reduce it, and for example, if we do something that's electron withdrawing, such as chloride ions, we see a easier to reduce. Okay. Actually, things aren't always so simple. Let's suppose we think about a molecule like tetraphenylethyline. You'd expect it would be similar to trans-stilbene. We've got, instead of one phenyl ring, we'll have 4, and we'll use shortcuts, use phi to indicate the phenyl ring. But in fact, what happens is not. As soon as that reduction occurs, there is a significant bending of the bonds, the twisting of the structure, because it turns out, because of the phenyl rings are there, they undergo some steric interactions, and so they twist away from planarity as soon as the double bond character is reduced by adding an electron to it. And so we get a little bit of a twist, and so the phenyl rings tend to twist away from being planar, and we see a change in the, so that makes it a slower rate of electron transfer. Another example where we have a simple outer sphere reaction that's slow is this one, this cyclooctatetrene. It's the stop sign shaped molecule. It turns out that it is not flat, as you might think, but in fact is tub-shaped if you look at it in cross-section. And in order to reduce it, we go to the radical anion upon reduction. In fact, the material is flat in this particular case. So we go from tub-shaped to flat, and so that internal rearrangement makes the reaction quite slow. Still an outer sphere reaction. There's still very little solvent interactions, but because we have to rearrange the bond structure, the lambda internal is very large. Another example of an outer sphere reaction in non-aqueous solvents is the reduction of oxygen and forming the radical anion of oxygen is also a simple one electron transfer process. Very little bond internal rearrangement, still linear molecule, but it has a very high solvent energy reorganization. Because we go from a small molecule that's neutral to a small molecule that's charged, there's a high solvent reorganization energy. So again, this tends to be a slow reaction in non-aqueous solvents. So outer sphere reactions are not necessarily fast. They depend again on the two things that Marcus tells us: inner sphere Our internal reorganization, such as cyclooctatetraene, is a good example. And oxygen, which is a solvent reorganization, also slow. But molecules that are simple, like transtylbene, which doesn't have large solvent reorganizations, or internal reorganizations, remain fast. Large rates of electron transfer. Okay. We're basically done with that chapter. That's chapter 3. And since we have some time here, what I thought we would do is go over briefly the problem set for chapter number 2, actually. And since you handed those in, I've handed those back to the people already, and they can follow along. Basically they did a good job, but I just want to point out a couple things that I might want to get to the people that are perhaps not doing the problem sets that for example, if they're doing it as an audit or something like that.